Hello 10th class students. So we are about to finish the current academic year as per the government guidelines. We are into the last chapter, current electricity. This chapter is very important for you in future, as well as in any competitive exam what you will be writing in the further studies. So do watch this particular video which I am giving you. These are the list of videos, and these videos are of very big length. Okay, so watch them again and again till you understand each and every concept clearly. I repeat, watch these videos again and again till you understand the concepts clearly.
Do you recognize the person you see on your screen? Yes, he is the great Thomas Edison. Do you know what he is known for? In 1879, he invented the first practical, long-lasting electric light bulb. And since then, our homes are bright even after sunset. You must be aware of the fact that lights in our homes work on electricity. However, they're not the only ones that use electricity. Our televisions, air conditioners, water heaters, fans, and so on also need electricity to function. Laser light or even small flashlights also work on electricity. Imagine a life without electricity in the world today. The discovery of electricity has helped to start a new revolution in the history of humankind. But let's just keep aside all the rhetoric talks and try to understand the real thing. I haven't really told you what the term electricity means. Well, there are basically two forms of electricity. One is static electricity and the other is dynamic electricity. For now, we are only interested in dynamic electricity. From the name itself, we can say that it implies moving electricity, or more precisely, moving electric charges. Now the next question you have will be, what are electric charges? The concept of electric charges is very important in physics, and it cannot be explained in a video or two. But I will still try to give you a short and to-the-point explanation of this concept. So let's begin. There are two types of electric charges. Positive, denoted by the plus sign, and negative, denoted by the minus sign. Think of magnets for a moment. We know that two like poles, that is, two north or two south poles of magnets, repel each other. And unlike poles attract each other. Similarly, like charges, that is, two positive or two negative ones, repel each other, and unlike charges, that is, a positive and a negative one, attract each other. But what exactly is charged? Or in other words, who actually carries these charges? Well, these charges are carried by tiny particles with incredibly small mass. They are called subatomic particles. The positive charges are carried by particles called protons, while negative ones are carried by particles called electrons. There are billions and trillions of protons and electrons present in any object around us. In some objects like metals, electrons can move randomly. While in non-metals, their position is kind of fixed and hence they cannot move freely. Now, any appliance in our house, for example a tube light, works because the negatively charged electrons are moving in the wire in one direction. This unidirectional motion of electrons in a wire is also called electric current. These wires are made of metal, usually copper or aluminium, and you can understand why. But why are the charges in a wire moving in one direction? Or what makes the charges move in the wire? The charges move in one direction in the wires because of the energy supplied to them by the transformers. So the transformer supplies energy, the charges move in a wire, which in turn makes our appliances work. A flashlight also works in the same way. But here the energy is supplied by the two electric batteries. So to sum it all up, dynamic electricity is flow of electric charges through conductors like, say, a copper wire. Generally, when we talk about electricity or electric current, we mean dynamic electricity. Hence, we simply say that electricity is nothing but the flow of electric charges through a conductor. In the next video, we will learn how to light up a small torch bulb using a single electric cell. So see you there. Imagine you have two beakers filled with equal amounts of water, and they are both connected to each other by a pipe at the bottom. If you observe the two beakers for a few seconds, do you think the water will flow from one beaker to another? No, you will see that the water in both beakers is as is and there is no flow from any beaker to the other. Now let me give you a task. Without changing the amount of water in any of the beakers, can you make water flow from beaker 2 to beaker 1? Understand my question again. You need to make water flow from beaker 2 to beaker 1. But you're not allowed to change the amount of water in any of the beakers. So you can't add or remove the water from any beaker. How will you do it? It's easy. One of the things you could do is raise the height at which the second beaker is kept. Once it's raised at a height, the water will flow from beaker 2 to beaker 1. What exactly happened here? What was the factor that made water flow? In simple terms, the factor was height. Yes, you can talk about gravity or pressure difference. But in layman terms, it is the height difference that causes the water to flow from the second beaker to the first. In an exactly similar way, for electricity to flow, there has to be some factor. We'll come to that factor soon, don't worry. So if we just have a copper wire, do you think electricity will flow through it? Clearly not, because there's nothing that's triggering it. There's no factor triggering it. So what is the factor that triggers the flow of electricity? It's called the potential difference. Now, I can't define this term in one line, but that wouldn't help you understand the concept well. So let's dive a bit deeper into it. We see the word potential here. Have you heard this term before? Of course, we've heard of potential energy. It is the stored energy when an object is at rest. When you're holding a ball in your hand, it has potential energy. When you drop it, the potential energy is getting converted to kinetic energy when it drops to the ground. Kinetic energy is the energy an object has when it's in motion. Similarly, there is a concept of electric potential energy. The electric potential energy of any charge describes how much stored energy it has. Just like the ball in your hand has high potential energy, a negative charge close to another negative charge has high potential energy. If left free, the charge will be repelled by the negative charge and will move towards the positive charge, just like the ball will fall towards the earth. What's potential difference then? It's just a difference of electric pressure between 2 points. And this difference may arise because of a battery consisting of cells. Potential difference is also referred to as voltage. If we have to understand the technical definition, we would say that it is the work done to move a unit charge from one point to another. The potential difference V between any 2 points in an electric circuit will be the work done over the charge Q. We know that the work is measured in joules and charge is measured in coulombs. What's the SI unit of potential difference then? It's volt, named after Alessandro Volta, an Italian physicist. So how would we define volt in a current carrying conductor? It is the potential difference between any 2 points when 1 joule of work is done to move a charge of 1 coulomb from one point to another. The potential difference is measured by an instrument called voltmeter. It's measured in parallel across the points between which the potential difference is to be measured. In the next lesson, we will solve an example related to potential difference.
Hello! What's going on, young scientist?
Hi, I'm trying to make an electric circuit.
Electric circuit? Wow! Have you learned that in school?
Yeah, a little bit. I have learned that the simplest complete circuit is a piece of wire from one end of a battery to the other.
Yes, an electric current can flow in the wire from one end of the battery to the other. But nothing useful happens. the wire just gets hot and the battery goes flat.
You are right. To do something useful with electric current, we need to put an electrical component into the circuit, such as a bulb, that can use the current to make something happen.
Very good. You already know quite a lot. Now, let's learn some more. When electric charges move in a wire, we say that an electric current flows in the wire. It's like the way a current of water flows in a river.
Yeah, it is like a constant flow of electrons through something.
When a wire is connected to each end of the battery, electrons begin to flow from negative to positive.
Yeah, from minus to plus.
And this flow of electrons is called current. Now look at this.
Hey, there is no battery in this.
Yeah, if there is no battery, no electricity will flow. So, the first condition for the flow of electricity in a circuit is that there should be something to make the electrons flow. Now look at this second circuit. What is missing?
Oh, the circuit is not complete.
Correct. This is an incomplete circuit. You need a complete path for the current to flow in. This is called an electric circuit.
So, you need some power source like a cell or a battery, and you need full circuit for electric charge to flow.
Yeah, here it is.
Look at my circuit. It has a battery and 2 bulbs, and it is complete with wires.
Yeah, it is very good. This kind of circuit is known as simple or series circuit.
Oh, so if this is a simple circuit, is this something called complex circuit?
There are 2 kinds of circuit, series and parallel.
So mine is a series circuit. Can you tell me about parallel circuit?
Hold on, my scientist brother. Let's first learn how to draw a circuit on a paper.
Oh, it's so simple. You need to make a picture of a battery and the bulb.
Yes, it is very simple. But in science, there are symbols for everything. Like for bulb, you draw a symbol like this.
Oh, then you need to draw 2, as my circuit has 2 bulbs.
And then the symbol for a cell is like this.
Oh, just 2 lines?
Now we need to draw lines. To make a circuit, we draw straight lines which take turn at right angles.
Now my circuit is complete. It looks so beautiful.
Like I told you, this is known as series circuit. Can you remove the wire from one side of the first bulb?
Oh no, both bulbs have gone off. What happened?
Everything was in the series. When one part of the series was removed, the circuit becomes incomplete and therefore the current stops flowing.
That is why both bulbs stopped working.
This is the problem with series circuits. Suppose if one bulb gets fused, all bulbs will go off.
Is there no use for this kind of circuit?
We use this type of circuit in Christmas or Diwali lights. One small bulb after another.
But if one of the bulbs goes off, all lights will go off.
And yes, there is another disadvantage also. If you will keep increasing the number of bulbs in this circuit, the light of each of the bulb will get dimmer than before.
Are there any benefits from this kind of circuit?
There are 2 benefits. One, it uses less amount of wires, and the second advantage is that if you want a warning that one of the components in the circuit has failed, then the series circuit is used.
Now I understand all about this simple circuit. Can you make a parallel circuit?
Oh yes, let's make a parallel circuit for you. Like I told you before, it requires more wires than simple circuit.
Wow, both bulbs are on. Can you remove one wire from the first?
Look, only one bulb has gone off. The second bulb is still on. Okay, now you have understood parallel circuit. Can you draw it on the chart?
Oh yes. Here it is. Is it okay?
Perfect! Let's clap for your work. Now can you tell me one benefit of parallel circuit?
Parallel circuits are useful if you want everything to work, even if one component has failed.
This is why our homes are wired with parallel circuit.
So even if one thing goes off, at least other things will continue to work.
You are a genius scientist.
I can tell the difference between series and parallel circuit in a very simple way. Can you please pass me the remote? Look, there are two types of highways here. One is a single lane highway and another is a parallel lane highway. A single lane highway is like a series circuit. One car stops and the whole traffic stops.
Very good example. And multi-lane highway is like a parallel circuit. Even if a car breaks down, the rest of the cars can keep moving. Very good way to compare both the circuits.
See, I am a genius. You can also become a genius. You should watch MakeMeGenius.com every day.
What do you understand by the word conduct? Well, in physics, it means transfer of something. And the materials that transfer something through themselves from one place to another are called conductors. That something could be anything. It could be heat, it could be electricity, or many other things. However, here we are interested in electricity. In this context, we will use the word electrical conductors. So now can we define it? You're right. Electrical conductors are the materials that transfer electricity through them. Or even more precisely, they are the materials that allow the electric current to flow through them. For simplicity, we will call them conductors. What are the examples of conductors? We have seen this simple circuit in the previous video. Here, a 1.5 volt cell is connected with a bulb which can be between 3 to 4 volts with the help of copper wires. So here I told you that the movement of electrons is from the negative terminal of the cell to the positive terminal. But however, by convention, the direction of electric current is taken to be from the positive to the negative one. But how exactly is the current flowing in the circuit? Or through which material is this current flowing? Yes, it's the copper wires. Electric current is flowing through the copper wires from the positive to the negative terminal. So what can we conclude from this? We say that the copper is a conductor of electricity since it allows the electricity to flow through it. Now, instead of copper wires, what if we use pieces of threads in the circuit? Will the bulb glow in that case? No, it won't. Why? Because the electric current cannot flow through a piece of thread. Such materials are called insulators. So how do we define this term? Give it a try. These are the materials which do not allow the electric current to flow through them. Let's study a bit about conductors first. Besides copper, what are the other materials that conduct electricity? Almost all metals conduct electricity. Silver, gold, aluminium, iron and mercury are a few other examples of metals that conduct electric current. If you replace copper wires in our circuit with aluminium ones, then you will find that the bulb is still glowing. This proves that aluminium allows electric current to flow through it. In fact, this area of the bulb is itself made up of metal. Hence, if we connect the wire anywhere in this region, the bulb will still glow. It transfers the electricity to the terminal of the bulb and inside. We can actually test any object for conductivity. Break the circuit up from anywhere by cutting the copper wire. Now at this point, I want you to notice one thing. Look at this region. There is nothing present in this region that can transfer the electrical energy from one side to the other. but there is air in this region. So what can you infer from this? This tells us that air is an insulator. It does not conduct electricity. Bring any object that you want to test, say this iron nail. Tie up both the ends of the wires at the two ends of iron and see if the bulb is glowing or not. If it glows, then it proves that the material that our object is made up of conducts electricity. Here the electric current is flowing through the iron nail. So our circuit is complete and the bulb glows. So this proves that iron is a conductor of electricity. Did you know that the human body is also a conductor of electricity? In fact, it's a very good conductor. This is the reason why we get an electric shock if we are not careful. The electric current flows through a body towards the earth. Now, which are the materials that do not conduct electricity? Materials such as plastic, rubber, cotton and wood do not conduct electricity. So they are insulators. For instance, instead of an iron nail, if we connect a plastic straw between the circuit, then the bulb will not glow. Do you remember what resistance is in an electric circuit? It is something that controls the flow of current. If it's more, then the current reading will be lower, and if it's less, then the current reading will be higher. It's inversely proportional to the current. Let's talk a bit more about resistance. What are the factors on which a resistance of a conductor depends? When can we say that the resistance of a conductor is more or less than that of another? Let's do a small activity to understand this. Take a small electric circuit like this one, which has a plug key, a power source and an ammeter. In the first case, connect a nichrome wire between these 2 points. Let the length of this nichrome wire be a lowercase l. Now plug the key and measure the reading in the ammeter. Now let's try playing with the factors a bit. In the second case, we double the length of the nichrome wire, but keep the thickness same. We just double the length. When you measure the reading, you will notice that the current is half of the current measured originally. When the length was doubled, the current halved. In the third case, we replace the wire with a thicker nichrome wire with length L. Understand this case well. We're just increasing the thickness of the wire without changing the original length L. Now, if you're increasing the thickness of the wire, it simply means we are increasing cross-sectional area. Let's call it A. Now, when you measure the current, you will notice that it's more than the original current I1. The results we're getting are pretty interesting. Let's try out one last case. We use a copper wire instead of a nichrome wire. The length and cross-section area A will be the same as the original wire, but the material has changed entirely. When you measure the current, you will notice that it's more than I1. Now let's understand the results case by case. We see that as the length of the wire increases, the current reduces by the same factor. It implies that the current is inversely proportional to the length of the wire. And by Ohm's law, we know that the current is inversely proportional to the resistance of the conductor. So these two together will imply that the resistance R is directly proportional to the length of the wire. More the length of the wire, more will be the resistance. Note that here we assume everything else will be constant. It'll be the same wire and it'll have the same cross-sectional area, and other factors like temperature will also be constant. So the length of the wire is one of the factors on which the resistance of a conductor depends. The resistance of a conductor is directly proportional to the length of that conductor. The third case tells us that as the thickness of the wire was increased, the current flowing through it also increased. It tells us that the current flowing through a conductor is directly proportional to the cross-sectional area of that conductor, which means that the resistance will be inversely proportional to the cross-sectional area of the conductor. Combining these two tells us that the resistance is directly proportional to the length of the conductor and inversely proportional to its cross-sectional area. If we introduce a constant ρ, it can be written like this. This is the constant of proportionality and is called the electric resistivity of the material of the conductor. In the fourth case, we saw that as the nature of the material changes, the current flowing through the conductor also changes. And that's because as the nature of the material changes, its electric resistivity also changes accordingly. Conductors, for instance, have lesser resistivity as compared to alloys, and alloys have lesser resistivity as compared to insulators. Nichrome is an alloy, while copper is a metal which is a good conductor of electricity. And that's why the current reading increased when the material changed to copper. The SI unit of resistivity is ohm meter. How is it ohm meter? We can look at this formula and deduce it. The unit of resistance is ohm, the unit of length is meters, and that of area is meter squared. Cancelling and transposing the units gives us the SI unit of ρ as ohm meter. We will understand resistivity in detail in the next video. But before we end this video, let's quickly review what we learned. The resistance of a conductor is directly proportional to its length and inversely proportional to its cross-sectional area. And it also depends on the nature of the material. If the material has low resistivity, its resistance will be lower, and if it has more resistivity, its resistance will be higher.
Particles with opposite charges attract one another. We can view this by saying that the positive particles that are far away from the negative particle have a higher potential energy, just as in the case of gravitational potential energy. Particles with the same charge repel one another. We again can view this as a case of potential energy. Although gravitational fields affect all objects in the same way, electric fields have an opposite effect on positive particles than they do on negative particles. From a negative particle's point of view, the potential energy throughout space is flipped upside down, as compared to a positive particle's point of view. Every charged particle contributes to shaping the electric potential energy at each point in space. The effect of each particle adds together. Suppose we have charged particles that are trapped inside a container. The charged particles will move to the edges of the container, causing the electric potential energy to be the same everywhere inside the container. If a container with charged particles experiences an external electric field, the charged particles inside the container will react by again moving in such a way so as to cause the electric potential energy to be the same everywhere inside the container. The charged particles inside the container will react by again moving in such a way so as to cause the electric potential energy to be the same everywhere inside the container. In a metal conductor, the positively charged particles are always fixed at one spot and unable to move. But the negatively charged particles are free to wander around. When the metal conductor experiences an external electric field, one side of the metal will end up having more negative particles than positive particles and develop a net negative charge. The other side of the metal will end up having more positive particles than negative particles and develop a net positive charge. Therefore, the effect is the same as in the example of charged particles inside a container. The electric potential energy is the same everywhere in the metal. In an electric circuit, the negatively charged particles flow through metal wires. Metal wires that are directly connected to each other with metal connections are all at the same electric potential. The difference between the electric potential energy of 2 points of a circuit is what we call the voltage. When a switch closes, it causes the two different parts of a circuit that it connects to be at the same potential energy. The number of charged particles that pass by each second is what we refer to as the current. When electricity was first discovered, it was not known that it is the negatively charged particles that move through wires, and it was incorrectly assumed that it's the positive particles that are moving in the opposite direction. The convention for how we describe the electric current's direction was never updated, and we therefore still refer to this situation as if it is the positive particles that are flowing in the opposite direction. Much more detailed information about voltage, current, and electric circuits is available in the other videos on this channel.
In the last video, we saw symbols of a few basic electrical components used in a circuit. This is a symbol representing a battery, which is a 1.5 volt cell. This bigger line represents a positive terminal and the small one represents a negative terminal. This symbol is used for the bulb connected in the circuit. It is just W written upside down in this way and enclosed in a circle. So if we were to draw this simple circuit using the symbols, then how would we do it? Just draw the symbols for the electric cell and the bulb first. Then using straight lines for wires, join them together. This is the circuit diagram representing this circuit. It was simple to draw, wasn't it? You can even show the direction of electric current in the circuit with arrowheads. So the electric current is flowing in this direction from the positive to the negative terminal of the cell. Now we had seen in the past that this is not the only way to light up a bulb in this circuit. For instance, if we interchange the wires connected to the two terminals of the bulb, then the bulb will still glow. This is because the circuit is still complete and all the terminals of the system are occupied. Can you draw the circuit diagram for this circuit? Why don't you give it a try? If you look at this circuit, the positive terminal of the cell, which was initially connected to this terminal of the bulb, is now connected to the other terminal. Similarly, the negative terminal, which was initially connected to this terminal, is now connected to this one. So how will the circuit diagram of this circuit look like? This is the circuit diagram. Compare it with this one. You see that we've just reversed the direction of the battery. Hence, the electric current in this circuit is flowing in the opposite direction. So the electric current can flow in either direction. As long as the circuit is complete, the electricity will flow and the bulb will glow. Let us look at this circuit now. How many components does this circuit have? Yes, 3. A bulb, cell and a switch. What is the symbol for switch? There are two symbols for a switch. This symbol is used when the switch is on and this symbol is used when the switch is off. If we were to draw a circuit diagram for this circuit, then here is what it will look like. Note that there will be two circuit diagrams for this. This one is when the switch is off and the electric current is not flowing through the circuit. We see that no arrowheads are shown here. This circuit diagram is when the switch is on. Here, the circuit is complete and the current is flowing. The arrowheads are used to show the direction of the electric current, which is always from the positive to the negative terminal of the battery. Now here is a question for you. We know that when the electric current flows between the two ends of the filament heats up. This heating up of the filament results in its glowing, and this is how we receive light from the bulb. But if this filament is broken, then will the bulb glow? No, it won't. This is because if the filament breaks, the circuit will be broken.
Magnetic field and magnetic field lines. A magnet only attracts the substances which have the metals iron, nickel or cobalt in them. Magnets are of two different kinds: natural magnets and artificial magnets. The natural magnets possess the ore magnetite in them. They are weak and often irregular in shape. When a natural magnet is rubbed against an iron or steel bar, the same property of attraction is communicated to these bars. These are then called artificial magnets. Around every magnet, there is a space in which the force of attraction or repulsion due to the magnet can be detected. This space is called the magnetic field. Let us see how the magnetic field around a magnet can be detected with the help of a simple activity. Let us place a magnet on a cardboard sheet. Now, uniformly sprinkle some iron filings over it. Did you see the iron filings arranging themselves in a definite pattern? Wow, isn't it amazing? This is because each piece of iron filings becomes a small magnet and experiences a force in a certain direction in the space around the magnet. These curved paths along which the iron filings arrange themselves due to the force acting on them in the magnetic field of the bar magnet are called the magnetic field lines. If the position of the magnet is changed, the arrangement of the iron filings also changes. Magnetic field and magnetic field lines. You would be amazed to know that the magnetic field around a magnet can also be traced using a compass. Wow, let us see how. First, fix a paper sheet on a drawing board by using brass pins and then place the compass needle near the north pole of the magnet. Now, observe the south pole of the needle pointing towards the north pole of the magnet and the north pole of the compass directing away from the north pole of the magnet. Then, mark the position of the two ends of the needle. Now, move the needle to a new position such that its south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet. And then, join the points marked on the paper by a smooth curve which represents a field line. Repeat the procedure for drawing many lines like this one. These lines that we have obtained represent the magnetic field. An arrow mark pointing from the north pole to the south pole indicates the direction of each magnetic field line. Let us now discuss the various properties of magnetic field lines. A magnetic field line has both direction and magnitude and is thus a vector quantity. Outside a magnet, magnetic field lines are directed from the north pole to the south pole. They are closed and continuous curves. The magnetic field lines are crowded near the poles and far apart near the center, thus imparting a stronger magnetic field at the poles as compared to the center where the magnetic field is weak. The field lines never intersect each other because it would imply two directions of magnetic field at that point, which is impossible. Parallel and equidistant field lines represent a uniform magnetic field. Magnetic field due to a straight current-carrying conductor. When a current is passed through a straight conductor, the magnetic needle placed parallel to this shows deflection. This is because a magnetic field is produced around a current-carrying conductor. This magnetic field can be traced with the help of iron fillings and a small compass needle. Take a thick conductor, copper wire XY, and pass it through the center O of the thick cardboard. Connect the ends of the conductor to the terminals of a battery through a rheostat, a key, and ammeter A so that the current flows from Y to X. Sprinkle some iron filling fillings uniformly on the cardboard. Close the key so that the current flows through the wire. Gently tap the cardboard a few times. We observe that the iron fillings arrange themselves in concentric circles around O. These concentric circles represent the magnetic field lines. Now place the compass needle at any point over the circles and observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire. When we change the direction of the current in the copper wire, the direction in the compass needle placed at a given point also changes. Now increase the current in the copper wire, the deflection in the compass needle also increases. This indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. But as we move the compass needle away from the conductor, the magnitude of the magnetic field decreases. Direction of magnetic field. Right-hand thumb rule. To find the direction of magnetic field due to a straight current carrying conductor, we use the right-hand thumb rule. The rule states, if a conductor carrying current is held in the right hand such that the thumb is pointed in the direction of the current, then the direction in which your fingers encircle the wire gives the direction of the magnetic lines of force around the wire. The rule is also called Maxwell's corkscrew rule. Suppose current through a horizontal power line flows in east to west. The direction of the magnetic field at a point directly above the wire is from south to north, but the direction below the wire is from north to south. Magnetic field due to a current through a circular loop. After Ørsted's discovery of magnetic effect of current carrying wire, Ampere found that a loop of wire also had a magnetic field. In order to find the magnetic field due to a current carrying circular coil, the coil is held in a vertical plane and is made to pass through a smooth cardboard at points A and B in such a way that the center of the coil lies above the cardboard. A current is passed through the coil and iron fillings are sprinkled on the cardboard. These iron fillings arrange themselves in a specific pattern in circular and concentric rings. The direction of the field lines can be found by applying right-hand thumb rule. At the center of the circular loop, the arcs of the big circles appear as straight lines. The magnetic field at the center of the coil can be taken to be uniform and also maximum, as the two semicircular segments of the coil through A and B assist each other. Magnetic field due to a current carrying solenoid. An insulated copper wire wrapped on a non-conducting cylindrical tube for example plastic, such that its length is much greater than its diameter, is called a solenoid. This is the pattern of the magnetic lines around a current carrying solenoid. If you compare the pattern of the fields so formed with magnetic field around a bar magnet, you will find them quite similar. In fact, one end of the solenoid behaves as magnetic north pole while the other behaves as south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid.